Dr. J. Glory. Today, I wish to tell about the Miller indices. So, before going to the Miller indices, we shall see the directions and planes of the crystal systems. So, coming to the directions of a crystal, in crystals, atoms are regularly arranged in space such that the environment about any atom is same. So, in crystals, atoms are regularly arranged in space such that the environment about any atom is same. So, there exist some directions and planes which contains large concentration of atoms. So, in the crystal systems, there exist some directions and planes which contains large concentration of atoms. So, for some planes, there may be high concentration of atoms, and for some planes there is low concentration of atoms. So, for some planes, so means that in crystal system, some planes may have a higher concentration of atoms and some of the planes may have lower concentration of atoms. So for giving directions and planes, we consider a two-dimensional Cartesian system. So that Cartesian system, here you can see in the diagram. So we have taken two-dimensional Cartesian system. So let O be the region of pattern. So in this figure, the 2D Cartesian system which have OA and OB directions. OA and OB directions. So directions generally assigned by the help of a first integer point. Directions are generally assigned by the help of first integer point x, y. XY. So, through which lines are passing. So, here the line is passing. So, in XY. So, in this integer point, we can represent. So, the line OA passing through the first integer point, x is equals to 1 and y is equals to 1. So, OA direction can be represented as 1, 1. So, similarly for OB also. Similarly for OB, we can tell the direction of the OB plane. So, OB is 2, 1. That is 2, 1 direction. In three-dimensional, it is represented by the first integer point through which line is passing. So, this is the three-dimensional Cartesian system. So, here x, y, z are there. X, y, z. Here, the directions can be represented as O be the region of pattern and from O, A. So, for the direction of OA on the plane of x, y, here the direction is 1, 1, 0. Direction is 1, 1, 0. Here and this. So, that's why we are taking in the x-axis there is an intercept and y-axis there is an intercept, but no in the y-axis, z-axis. So, that the direction of the crystal plane is OA is equals to 1, 1, 0. As like when we are taking the direction of OB, when we are taking the direction of OB, here at B, we have the intercept so that OB is equals to 0, 1, 0. Like in the OC direction, it is 1, 1, 1. OD 2, 0, 1. 2, 0, 1. This one 1, 1, 0 in the OA direction and OB direction 0, 1, 0. OC direction 1, 1, 1. OE direction 2, 2, 1. Likewise, if we take OF direction it would come 1, 0, 0. In the in the OG direction, O, 0, 1. OG direction, it will be 0, 0, 1. So like that, we can tell the directions of the crystal system. So in crystal systems, so we see that lattice planes. So the crystal's lattice may be regarded as it is made up of aggregate of a set of parallel equidistant planes passing through the lattice points. So in the figure you can see that the crystal lattice, this is a lattice. So lattice is nothing but atoms, a points which represents the atoms. Okay, so instead of atoms we are replacing with the points in 2-dimensional or 3-dimensional. So then it represents the lattice. Okay, so here crystal lattice, this is the crystal lattice. So crystal planes may be regarded as it is made up of aggregate of a set of parallel equidistant planes passing through the lattice points. So here in this lattice, the line is passing through the lattice points. So each point is a lattice point. It's completely lattice. So crystal lattice, in this lattice, each point represent as a lattice point. So here a plane is passing through the lattice point. So this plane is passing through the lattice points. So how many lattice points it is passing? So 1, 2, 3. So it is, the plane is passing through the 3 lattice points. So likewise, there are so many number of planes passing through the lattice points in different directions. So what we are telling in the definition, the crystal lattice may be regarded as it is made up of aggregate of set of parallel equidistant planes. So this is one plane, and there is another plane. So in this directions there are 3 planes are there, and coming to the perpendicular direction, so 1, 2, 3, as like we can see many number of crystal planes. So the planes which are passing through the lattice points, when comparing to the other crystal planes, there is equally distant. So that is the plane. So the crystal plane which are passing through the lattice points. So when we are comparing to the other plane, so the distance will be the same. Aggregate of set of parallel equidistant planes. So these are parallel planes, and these are set of parallel equidistant planes. So when you are taking the distance between the 2 parallel planes, the distance is same. So here if we take the distance between these 2 planes is d. So here the distance between these 2 planes also be d. So a set of parallel equidistant planes passing through the lattice points are known as crystal lattice planes. Okay, so crystal lattice may be regarded as it is made up of aggregate of set of parallel planes which are passing through the lattice points are called as lattice planes. So the lattice planes can be chosen in many ways, as like in the picture. Okay, so this in this direction it is passing through these points. So these are the parallel planes. We can write a many number of planes. So in this direction we can write like this. Okay, and also like this. So set of parallel planes which are equally spacing, Okay. So lattice planes are generally parallel and equally spaced planes. Lattice planes are generally parallel and equally spaced planes. So generally the lattice planes are characterized by the Miller indices and interplanar distance or interplanar spacing HKL and D respectively. So HKL is defines that it tells that crystal plane, lattice plane, and D is representation of representation regarding to the interplanar spacing or interplanar distance. So each family of lattice planes have an interplanar spacing which is denoted with D. So it is necessary to locate the directions and planes for its analysis. So to analyze the crystal system, it is necessary to locate the crystal directions and planes. So in a crystal lattice, the directions are given by the coordinates of a first whole number point. So when we are taking 2D Cartesian system, so the direction of OA can be represented as 1, 1 and OB, the direction is 2, 1. So coming to that 3D, so the directions in different ways will be like this. So now we shall see the Miller indices. So Miller indices, we can now know about the Miller indices. So here we are considering a two-dimensional lattice. In Miller indices, we are considering a two-dimensional lattice with a periodic array of lattice points. Periodic array of lattice points. There is a two-dimensional lattice with a periodic array of lattice points. So the plane passing through the lattice points is known as crystal planes, as before we have seen that the plane passing through the lattice points is known as crystal plane. The perpendicular distance between two adjacent crystal planes is called interplanar spacing. In crystal lattice, these interplanar spacing is same. Okay, so the crystal planes can have different orientations. So here in the crystal plane, so in the lattice planes here, these planes are in different orientation. This would be in this horizontal direction and this is in the vertical directions, like that. It has many number of orientation. So crystal planes can have different orientations. So the crystal planes is represented by three smallest integers which are known as Miller indices. The crystal plane represented by three smallest integers is known as Miller indices. So Miller indices are three smallest integers which have the same ratio as the reciprocals of the intercepts of the crystal plane with the coordinate axis. So Miller indices are three smallest integers which have these three smallest integers have the same ratio as the reciprocals of intercepts of the crystal plane with the coordinate axis. So how to find the Miller indices? So procedure to find the Miller indices. So the intercepts made by the crystal plane. The intercepts made by the crystal planes along x, y, z axis have to write in terms of lattice parameters A, B and C. So we should note the intercepts made by the crystal plane along XYZ axis in terms of lattice parameters ABC. As before that, before in previous sessions, we discussed about this lattice parameters. So lattice parameters are ABC, that is dimensions and interfacial angles, both called as lattice parameters. So these ABC also called as primitives. So these primitives gives the dimensions of the crystal. Okay, so first to find the Miller indices, the first step we have to do is we have to note the intercepts. We have to note the intercepts which is made by the crystal plane, along XYZ axis, that should be written in terms of lattice parameters A, B and C. Next, in the second step, express the intercepts as multiples of A, B, C. So we have to express the intercepts as multiples of A, B and C. Then in the third, take the reciprocals of the intercepts. So in the third step, we have to take the reciprocals of the intercepts. Then we have to convert the reciprocals into integers by multiplying each one of them with the LCM. So convert the reciprocals into integer. Next thing, how we can convert this reciprocals into integers is by multiplying each one of them with the LCM. Then finally, enclose these integers in smaller parentheses. We have to enclose these integers in smaller parentheses. So then this represents the Miller indices of the crystal plane. This represents the Miller indices of the crystal plane. So these are the steps we have to do to find the Miller indices. So we have to take some example, then we can see clearly that we can understood. So here, for example, I'm taking here ABC. ABC is the crystal plane. ABC is the crystal plane. So the intercepts on the crystal plane is 2A, 3B and 2C. 2A, 3B and 2C. Along XYZ axis. Along XYZ axis, where ABC are the lattice parameters. So first step is we have to note the dimensions of the crystal plane. So that I'm taking ABC as a crystal plane. Here ABC is a crystal plane and this plane is intercepting on XYZ axis on 2A, 3B, 2C. 2A, 3B and 2C. So here 2A, 3B, 2C, this A, B, C called as lattice parameters. Then in the second step, the intercepts as the multiple of ABC. The intercepts as the multiples of ABC are 2, 3, 2. The reciprocals of the intercepts can be written as 1 by 2, 1 by 3, 1 by 2. Then we have to convert into integer. So now I'm taking the LCM. So the LCM is 6. Then we'll get the integer 3, 2, 3. So the integers are written within parentheses as 3, 2, 3. So this 3, 2, 3 represents the Miller indices of the crystal plane ABC. So the first step 1, we have to note intercepts. We have to note the intercepts on X, Y and Z axis. This is the first step. So this can be written in terms of lattice parameters. That's why in terms of lattice parameters, the interceptions on the ABC crystal plane is 2A, 3B, 2C. Okay, so in terms of lattice parameters, we have written the intercepts 2A, 3B and 2C here. Then in the second step, intercepts the intercept as the multiples of A, B, C or 2, 3, 2. So here I have written here 2A, 3B and 2C in terms of lattice parameters. Then in the second step, we are writing only multiples of these lattice parameters. That is, the multiples of lattice parameters is 2, 3, 2. The multiple of A is 2, multiple of B is 3, multiple of C is 2. So the multiple of lattice parameters is 2, 3, 2. Now in the step 3, take the reciprocals. When taking the reciprocals, so 1 by 2, 1 by 3, 1 by 2. Then in step 4, have to convert it into integers. So convert it into integers. To convert it into integers, we have to take the LCM. So LCM of this is 6. So here 2 3s 3, 3 2s 2, 2 3s 3. So 3 2 3, 3 2 3. In the fifth step, step 5, have to represent this 3 2 3 in the parenthesis. This integer in parenthesis. So 3 2 3 we got in step 4. So represent with the parenthesis. So this represents the Miller indices of the crystal plane ABC. So we can see through some diagram. So here X axis, Y axis and Z axis. So crystallographic axis. So X, Y, Z are the crystallographic axis. So crystallographic axis. Now the intercepts on the plane, on the axis, on the crystallographic axis, on X axis, the interception is 2A. On X axis, it intercepts at the point 2A. On Y axis, the interception is This is y-axis. The interception is here, that is at 3B. 3B. On z-axis. The intercept is the z-axis. The interception is here at 2C. 2C. So these are the intercepts on XYZ have written in terms of lattice parameters. So that the intercepts are 2A, 2B, 2A, 3B and 2C. So take the multiples of A, B, C. So 2, 3, 2. 2, 3, 2. Okay. Now take the reciprocal. So 1 by 2, 1 by 3, 1 by 2. Now converting into integer. So by taking the LCM. LCM is 6. So that taking the LCM, we are getting 2 3s, 6. So 3. So 3 2 6. So 2. So 2 3s, 6. Now have to represent in parenthesis. So 3 2 3. So this represents the crystal plane. So this is the Miller indices. So Miller indices of the crystal plane, which is for A, B, C. So this is the plane. So the plane is intercepting. The plane is intercepting on the crystallographic axis A, B, C with the dimensions of 2A, 3B, 2C. So for this crystal plane, we determine the Miller indices. So we have to note some points related to this Miller indices while writing this Miller indices. A comma or dot between any two numbers may be avoided. We should not put any dot or comma. Suppose before that we have written 3 to 3 in parentheses like this only. Like this we have represented the Miller indices. So we should not write any comma. We should not put any comma, or else we could not put any dot. We should not put any dot like this. We should not put any dot or any comma between the numbers. So we should write only 3 to 3 like this. So this shows Miller indices. Okay. So while writing Miller indices, a comma or dot between any two numbers may be avoided. We should not write any comma or dot between the numbers. The positive x-axis is represented as 100. Crystal plane 100. Okay. The positive x-axis is represented as crystal plane 100. On y-axis 010 and in z-axis 001 if we take 3 dimension. Similarly, if there is a negative x-axis, then it can be represented as 1 bar 00 on y-axis, that is negative y-axis 1 bar 0 and negative z-axis is 001 bar. So the Miller indices for a plane 101 is read as 101 and not as 101. We should not write 101. We should not read like 101 as usually habitual. Okay, so we should read this crystal plane. This Miller indices of a plane is 101. Like that we have to read. So these are the Miller indices of various crystal planes in unit cubic cell. Various crystal planes in a cubic unit cell. Suppose here XYZ, this is a cubic unit cell. So here we have taken the 001 plane, 001 plane, so that it intercepts at the Z axis. So this source X, Y, Z. So on Z axis, the interception is 1. So that there is no interception on X axis or Y axis. No interception of X axis and Y axis. So this is the plane. So this plane we are taking. So when taking this, the crystal plane can be represented, that is the Miller indices can be represented for this crystal plane of a unit cubic crystal is 001, as no interception on Y axis, no interception on the X axis. So only there is interception on the Z axis. So that can be written as 001. So in this case, so no interception means infinity. No interception means infinity. So that we can write this Miller indices infinity, 1. Okay. So here we take the reciprocal 1 by infinity, 1 by infinity, 1 by 1. So it will be 001. So representing in parenthesis, this shows Miller indices. This is the step to find the Miller indices. Okay. So like the same here in the second diagram. So X, Y, Z, the interception on the X axis. The interception is on X axis. Here it is intercepting. So 1. So on X axis 1. For Y axis, so this is the plane we are taking. This plane, front one. Okay. So no interception on the Y axis. So Y is equals to infinity. And on Z axis, there is no interception. So infinity. So take the reciprocal 1 by 1, 1 by infinity, 1 by infinity. And convert into integers. So 1, 0, 0. So represent in parenthesis gives the Miller indices 100. As like the same here in the third diagram also. So the interception is only on Y axis. So that 0, 1, 0. X is equals to infinity. Y is equals to 1. Z is equals to infinity. For the third diagram, X is equals to 0. Y is equals to infinity. X is equals to infinity. Y is equals to 1 because there is an interception on Y axis. And Z is equals to no interception. So infinity. Then take the reciprocal 1 by infinity, 1 by 1, 1 by infinity. So 0, 1, 0. So representing in closed parenthesis gives the Miller indices. Okay. So for negative axis, so or here we can take this diagram for negative axis. So for negative axis, here the interceptions are, on y there is an interception, on z also there is an interception, but x is inwardly there is an interception. So this plane, crystal plane, a representation of Miller indices is 1 bar 1 1, 1 bar 1 1, like that. For negative axis we can represent the Miller indices as it is inward, x is inwardly here intercepting, so that we are taking 1 bar, but remaining are in positive, but only x axis it is a negative axis it is intercepting, so that 1 bar 1 1. So we can take this one 0 1 1 plane. So in this 0 1 1 plane, what happening? So on x axis no interception, as the crystal plane is this one. So the crystal plane x axis no interception infinity, y axis here the interception take as 1, and z axis here there is an interception, so 1, so that 1 by infinity, 1 by 1, 1 by 1, then 0 1 1, 0 1 1 is the Miller indices for this crystal plane. So important features of Miller indices of crystal planes. So Miller indices represents the orientation of crystal planes in a crystal lattice. So what it represents? It represents the orientation of crystal planes in the crystal lattice. And any plane parallel to one of the coordinate axes, any plane parallel to one of the coordinate axes will have infinite intercepts. And the corresponding Miller index is 0. So any plane parallel to one of the coordinate, axis will have infinite intercepts. So suppose if we are taking here, so this is parallel to z plane, but here it has infinite of intercepts. Okay, so here we can take on z axis, here this in this z axis, so in the 0 0 1 plane, here the interception is on z axis, so the interception only be at the z axis here, but when coming to the y direction and x direction, there is no interception. So in this case, the interception is infinity. But here the interception for as, because it is a cube, I am taking 1, because all the dimensions in a cube is same. So I am taking 1. So that any parallel plane to the coordinate axis will have infinite intercepts. So the intercepts is infinite intercept on the x-axis, infinite intercepts on the y-axis, and on z-axis the interception is 1. So that when taking when calculating or doing the steps of Miller indices, we are getting Miller index as 0. So as here the interception on x-axis is infinity, so that when finding the Miller indices, we are taking the reciprocal, so 1 by infinity becomes 0. So the Miller index becomes 0. So that we are getting 0 0 1 here. So this is for the first diagram. Okay, so the interception, so this is This is a plane parallel to the x. So that no interception. So that is infinite interception on x-axis. Infinite interception on y-axis. So that x is equals to infinity interception, y is equals to infinity interception, but z is equals to 1. When taking reciprocal, 1 by infinity, 1 by infinity, 1 by 1. So that 0, 0, 1. That's why we are telling here, any plane parallel to one of the coordinate axis will have infinite intercept and the corresponding Miller index is 0. If the Miller indices of the planes have a same ratio, then the planes are parallel to each other. Parallel to each other. So if the Miller indices of the planes have the same ratio, then the planes are parallel to each other. Suppose we can write 2 is 2, 1, 1, the ratio. 4 is 2 is to 2. So the Miller indices of the planes which have the same ratio. So these two are the same ratio, then the planes are parallel to each other. If I'm writing like this is intercepting here, and so Miller indices of the planes have, so these planes are parallel to each other. 1, 2, 3. So these planes are parallel to each other. So the Miller indices of these planes having the same ratio, when writing this Miller indices. Okay, so if the Miller indices of the planes have the same ratio, then the planes are parallel to each other. Okay, so planes with negative intercepts are represented by a bar. So 1 bar 0 0 like this. So this indicates that the plane has an intercept in the negative axis. Here only the x-axis is intercepting at 1 negatively. Okay, so this invert, that is 1 bar, represents the interception is made on the axis x invertly. Okay, if HKL is the Miller indices of a crystal plane, then the intercepts made by the plane with the coordinate axis are A by H, B by K, C by L, where A, B, C are the lattice parameters or primitives. So if HKL is the Miller indices of a crystal plane, then the intercepts made by the plane with the coordinates can be written as A by H, B by K, C by L. So where A, B, C called as lattice parameters or lattice parameters or primitives. So this is about the Miller indices. And the cubic crystal. For a cubic crystal, the interplanar spacing between the adjacent parallel planes is D is equals to A by root of H square plus K square plus L square. So interplanar spacing. So here lattice planes, crystal planes, we can say that a set of equidistant parallel planes passing through the lattice points is called the lattice planes. So the distance between the two adjacent planes or C, D. So this D interplanar spacing is D is equals to A by root of h square plus k square plus l square. This is for cube. The interplanar spacing for a cubic crystal. But for others, it would be vary. As cube have the same dimensions. That's why A is equals to B is equal to C. In that case, all the dimensions are same. So that D is equals to A by root of h square plus k square plus L square. So where A is the lattice constant, HKL is the Miller indices of the crystal plane. So for a cubic crystal, this HKL is equals to A by P is to A by Q is to A by R. For any crystal, this would be HKLB, A by P, B by Q, C by R, as the dimensions are different for any other crystal. But for cubic crystal, the dimensions is same. That's why we have noted A. So this is about the Miller indices, and in the next class we shall see the other topic, interplanar spacing. We shall discuss about the interplanar spacing. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.